what's the aim of this presentation is to provide an overview of the practical principles underlying DFT computations and how it can be connected with the experiment. So our aim, after all, is to understand chemical phenomena at the atomic scale. And once we have this detailed understanding at the atomic scale, we can apply it in real case scenarios. So computations predict, and once we have a good prediction, we can test it experimentally. So this is the overall aim of the presentation, in fact. All right. So in doing so, we define DFT. It is the density functional theory. It is a branch of quantum chemical calculations. So to run the calculations, we need the algorithm, which is the software basically. We need the machine. Then we need to look into the application. So what the DFT does, it predicts the properties of the molecule based on the determination of the electron density. I think if you look at any molecule or any atom, for example, if you take water, we know that the charge on the oxygen is -2, but in fact, it is not exactly -2. Electron does not exist as discrete amounts or discrete quantities. They are more like a cloud, and this is what we call the density functional of the molecule. So the functional is defined. It's basically try to answer the question where the electrons are. Once we know where the electrons are, we can compute all other properties. So DFT is really a computer experiment. So instead of going to the lab, you can do the experiment using your computer. So we can obtain properties that we normally obtain at the lab. For example, the enthalpy of the formation, or the adsorption energy, or the lattice constant, or the reaction rate constant, or the heat capacity, or the entropy, or the diffusion rates, any other properties that can be measured. So when we say experimental, so why do we do DFT? Because it's much cheaper than to do the experiment. So experimental analysis in many cases is too expensive or it's not practical. For example, if you'd like to measure the heat capacity at a very high pressure, for example, 100 bar, then it is not safe to do the experiment at 100 bar, but we can do it with DFT almost with a zero cost. So there is no cost to DFT, I mean, except buying the software and finding somewhere to run the calculation. So most of the DFT calculation, as we know, they are run at high performance computer, and in many countries they assign like computational centers where people can install their DFT softwares and run those calculations. I mean, if you look at any publications in top journal, most likely it will have a DFT element to it, where it tries to explain the experimentally obtained results. So DFT have become a common feature of journal articles in all branches of chemistry, materials, chemical engineering in general, and they are used to electronically characterize the molecule or to look deep into how the reaction takes place. So nowadays, the spread of user-friendly quantum chemistry software has aided to spread the use of the DFT. And this graph here shows the number of articles published in those top ranked journals where DFT have been used. So when we talk about DFT, it's very important to talk about the scale. So we talk about the electronic scale, in fact. And what we obtain at the electronic scale, it is scalable at the scale that we see. For example, in DFT, we measure the properties of one molecule, but in real life, we deal with big quantities like mole or gram or kilogram or 1 centimeter. So whatever properties we obtain using DFT are also scalable to real case scenarios. So while the tool in DFT comes from physics or chemistry, The question that we try to answer are truly fundamental. For example, what is the rate of the formation of the pollutants, or how to enhance the absorption of pollutants, and so on. So there are a wide spectrum of applications. So those the two scientists who got the Nobel Prize in 1988 who developed the DFT that we know today. Everything is based on the quantum mechanical description system. This is the basic equation. Actually, it's much more complex than this. If you refer to a textbook in quantum chemistry, or you will get a clear idea of the sophistication inside the DFT. But this is everything starts from here. This means that this is the wave function, which is where the electrons are, and this is the energy. So in fact, we are trying to minimize the energy for the system or the molecule or the lattice based on the electronic arrangement, so that we know why there is, for example, if you look at the CO2, it is a linear molecule. If you look at H2O, there is an angle. So why do we have an angle in H2O and we have a linear molecule in CO2? Because this is the minimum energy structure in the two cases. And those are the terms that the DFT calculates. It calculates the nuclear kinetic energy, the electronic kinetic energy, the electron repulsion, and so on. So there are many terms to obtain. So in DFT, we mainly calculate the exchange. There are many DFT methods, but all of them have some common terms. All these are common terms, except this one. This one is what we call the exchange correlational. So different DFT methods apply different exchange correlational for a particular system. And the commonly used one belongs to one of those four families. It is the local density approximation, the generalized approximation, and the hybrid exchange. So here the difference is only in this term, the exchange correlational. Actually, so what this term, it's right to treat the exchange or how the electron interact with each other inside a molecule. So this is, I mean, in fact, if you look at an ionic system, we know that we describe it as many-body perspective. Like we have one electron. This is where the electrons are. But this is not. This is an oversimplification. What happened in reality? We have a cloud of electrons that we call it the electron density. For example, if you look at the picture of this horse, it looks very well organized. But this is not. This is a real horse. But for example, if I assume this is my molecule, I would have this picture of my molecule. But this is not the case. What we have a density where the electrons are distributed between the atoms or between the different structural entities. Anyway, I mean, our aim here is not to explain how the complex mathematical formulation behind DFT, but it is only to give an overview of the terms inside the DFT. So if someone is interested to know the very complex mathematical formulation in DFT, they can refer to many textbooks like these ones or different journal articles. Now I'll move on very quickly to the practical thing. So what can we get from DFT, or we can train the students in the lab to get? Like especially in the COVID, in the first 2 years of COVID, students were not able to go to the lab to do real experiment. But here in my university, we did a virtual lab where students can still measure properties that they can obtain in the lab. For example, if you are looking for electrical properties, that the conductivity or what is the capacitance, then we can use DFT. Sometimes we use DFT to obtain optical properties of the material, like the polarization of the absorbance constant or transmittance or so on. We can also use it to get the magnetic properties. For example, the magnetic moment Most importantly, in my case, as a chemical engineer, I train my student to use DFT to calculate thermal properties. For example, heat, heat capacity, thermal conductivity, melting point, and so on. We can also use DFT in case of, this is more for material, people who work on materials. They can use DFT to calculate, for example, the modulus, the modulus constant, or the compressibility, or the hardness, and so on. Also, chemists are often use DFT, or I train my students to use DFT to calculate chemical properties. For example, the bond dissociation, enthalpy, the affinity, the dipole moment, reaction rate constant, enthalpy of formation, and so on. So in general, we can use DFT to obtain 5 categories of properties, either structural, electronic, magnetic, optical, as well as vibrational ones. So here we look at the at the bigger picture. Normally, for example, let's assume that you would like to know if the material can conduct heat or electricity, or it's a semiconductor, or it's an insulator. We can use DFT to calculate the band gap. The band gap, it is this region where electron cannot be transferred based on the electron density. So if you are on the chemistry or the chemical engineering side, DFT can be used to understand the combustion chemistry of fuels. We can use it to design new materials. We can use it to construct very complex chemical mechanism, or to obtain thermochemical properties like the heat capacity, or the entropy, or the Gibbs free energy, and so on. So these are the main use of DFT in case of for chemists and chemical engineers. So DFT has been used in chemical engineering to calculate properties that related to the chemical safety of a compound. For example, the ignition delay time, or the combustion energy. Or you could also study the behavior of materials in fire, and what type of pollutants that they can emit. For example, if you have a plastic material and you would like to predict what are the pollutants that might emit from burning this plastic material, then DFT can be used to draw the mechanism, as well as to calculate reaction rate constant. And from the reaction rate constant, we can establish the kinetic model. Well, these are the software that normally students use to use DFT. In fact, there are many softwares, but these are the most used one. Gaussian is used in gas phase calculation. VASP, it's used for material. CASTAB, it's similar to VASP. So it's used for material. So some of these software are very easy to learn, like Gaussian. Some of them they need a bit of learning curve, for example, VASP. But all these are Unix software. Gaussian comes in 2 versions, Unix and Windows. So if you are looking for molecules, you can use Gaussian. If you're looking for materials, you can use either VASP or CASTAB. I mean, nowadays students who they study reaction engineering, or they study catalysis, they often are trained in the lab to look into new materials, like cutting edge material, and one of those are metal organic frameworks. It's the MOF. So a student can learn how to construct a mechanism for the action in a MOF. They can study the chemical conversion as well as adsorption. This is the starting point. If you look at this figure, this paper is this is the starting point, and this is the end. So this is what is called the potential energy surface. It describes how the reaction occurs from A to Z. And such type of information we cannot obtain experimentally. That's why students are trained to calculate the activation energy, the reaction energy, and to draw the map. This is like a roadmap for the entire reaction. And this could be only obtained by DFT. Also, we can use DFT, or a student could be trained to use DFT to design new catalysts. For example, if you'd like to maximize the selectivity, you could start with 100 candidates for compound. But since it's very expensive to test all these experimentally, we can focus on a few of them. We can do the testing in DFT, and once those that we obtained from DFT shows promising application or promising outcomes from DFT, you can prioritize them to or shortlist them to be tested experimentally. So before we go to the lab, we can check the catalyzed reaction using DFT. For example, let's assume my aim is to convert phenylacetylene into styrene. It's a very important reaction in hydrocarbon industry. So like we know that 100 compounds, 100 catalysts might do the work, but it's very expensive to test all of these 100 catalysts for this particular reaction. So we do the experiment in DFT, and we shortlist the catalyst that might give us optimum performance. And then once we determine those promising catalysts, we can go to the lab. So DFT saves money in this perspective. So we can also use DFT to study to obtain thermomechanical properties of material. As I said, here, for example, we calculated the heat capacity at very high pressure. And so on. Sorry, I can't remember this one. Yeah, so a student could also use DFT to obtain adsorption energies. And they can use it to establish properties of or to design new materials. It could also aid in the design of new polymers. Also, we have published a paper on where DFT can be used or where it can be introduced into the chemical engineering curriculum. So we integrated DFT in 2 courses. The first one is reaction engineering, and the second one is catalysis. So we basically design virtual labs for those ones. So as I said before, it's very important to make a connection between the experiment and the theory. So we use we focus on combustion and catalysis. And at the end of the day, we need to validate our result or to explain why do we have this type of result. For example, the formation profile of compounds, or for example, the generation of H2 or any other thing. So we do the experiment in the lab, and then we do the validation and molecular understanding using DFT. So for example, we measure the chemical composition using GCMS. Sorry, I'm not sure if you can hear me now. Hello?
Yes, yes, we can hear you.
Sorry for that. Okay. So we can also use DFT to predict. So DFT predicts, and basically the experiments confirm. And one of the most important applications of DFT is to obtain properties at very high temperature and very high pressure. So those experiments cannot be done in the lab. That's why we have to use DFT for it. For example, people who design the vaccine for COVID, all these pharmaceutical companies, they use some types of molecular modeling to study where those active ingredients in the vaccine can attack the protein of the virus or the RNA. So those are the protein components in the virus or any other virus, and to design a vaccine or to design a medicine, or one of the most important steps is that this vaccine should or this antiviral should have the capacity to attack the molecule at certain locations. And so this is one of the promising applications for DFT. It's to design new drugs and new vaccines. Of course, in doing the calculations, we have to establish a benchmark of accuracy.
Hello, Dr. Mohammed. Are you there? We are not able to hear you. Can you please check if you are talking on mute?
Yeah. Is it okay now?
Yeah. It is audible now. Yeah, thanks.
So before we report the result from DFT, or to give students confidence that this DFT will work, we have to report a benchmark of accuracy. So this benchmark of accuracy, the result obtained from DFT has to be within 1% of the result. So we choose an experimental value. Let's assume I am doing experiment on this catalyst, alumina. Alumina is used as a support in catalyst. So if I do the DFT calculations, I have to make sure that my DFT gives me a reasonable agreement with the experiment, because at the end of the day, we believe in what we see in front of our eyes. We believe in the experiment. The DFT is just an explanatory tool. So if I do the DFT calculation, I found that the lattice parameter, for example, this value. So when I do the experiments, I will find a difference that within 1%. So a difference of only 1% will give me a confidence that my other obtained results should be accurate. So this is in terms of geometry. In terms of other properties, it has to be within 5% of other properties. So how accurate in terms of other things? When we do a DFT, we need to set a benchmark of accuracy. As I said, it could be a band gap if you are working on materials. It could be a reaction rate constant if you are working on chemical reactions. It could be enthalpy of formation if you're working on the thermodynamics. It could be IR spectrum if you are working on chemical analysis of things. So how do we present the material? We present material either as a surface, or as a cluster, or as a molecule. So this is how the material is presented. It is either a surface, a cluster, or a molecule. So what's the ultimate goal? The ultimate goal is in DFT is to find the minimum energy structure. So this is the algorithm for DFT. This is what students implement. We start with a known geometry. Then we define the initial position, and then the software or the calculation algorithm try to find the minimum energy structure. So if this minimum energy structure is found, then it proceeds to calculate the properties. Otherwise, the procedure repeats itself until a minimum energy structure is obtained. So this is how the students are trained. So what do we need? What students need to have? We need to have an initial geometry. We need to have a Gaussian-like basis set, and we need to specify the method. So what is the basis set? Basis set, it's basically a mathematical description of the orbital in the system. It could be a simple one like a Gaussian, or it could be a very complex one. So basically, it's like a linear combination of the molecular orbital, and the larger the basis set, the more accurate the results are. But however, the slower the calculations are. So there is a trade-off between accuracy and cost. Cost means the computational time. This slide, I don't think it's visible, but it shows how many, the type of basis set. So there are hundreds of them, and so those ones are well tested. So we don't need to test them again. So as I said before, there is always a trade-off between accuracy and time. So if in doing the DFT, one need to build the initial structure. There are some free softwares to build the structure where a student can use them freely, and some of them are commercially available. So if you are building gas phase molecules, this one is Avogadro, it's an open source. Gmol is an open source. If you are building a material, then Vista is an open source. This one is commercial, it's very expensive. Gaussian view is also commercially available. So before we do the DFT calculations, we need to build the molecules. So when we build the surface, we need to, students are trained to get it from crystallography database, and then they cut the surface at one of those similar indices. So each DFT codes read different format of the structure. However, the crystallography information test system, this one is the most common one. So everyone convert them into this format, and then it is reconverted into any other format that is required by the surface. So before the student apply the DFT, they need to specify the termination of the surface. For example, if we look at this material, we have different termination. Different terminations mean what are the atoms are exposed at the surface, and catalytic reactivity are basically determined by the type of the atomic termination. So which DFT methods? So those DFT methods come in different flavors, and students should be careful what to choose based on which one will give us a more convincing comparison with the experiment. I mean, we could have a combination of them, or we could have standalone functional, but at the end of the day, we don't need to test them. The students could be told to read relevant research paper and follow what kind of DFT methodology that paper has used for in a similar applications. I think here the message that we need to convey to the student is that it's very important for them to validate the DFT against an experimental value that it is relevant to the system that they wish to study, because different methods may give opposite results. For example, this one gives the enthalpy of a reaction using different method. For example, this method gives an exothermic reaction. However, if you apply another method, you will have an endothermic reaction. So which determine is it endothermic or exothermic? It is the experiment. And people who are working on graphene, for example, they would be very interested to calculate the lattice constants in the graphene based on different methods and so on. So here, it's very important to validate it. So which DFT method that students should use? There has been a great deal of wisdom has accumulated in the literature for nearly all possible systems. This should give student a guide which particular DFT methods work better for in a specific system and so on. As always, rejection or acceptance of any DFT paper largely depends on the methodology section. So students should be trained to write these sections very well. Since we don't have much time, I will jump to a catalysis case. Which is this one. So in this paper, students calculated a pathway to generate hydrogen from water dissociation on a zirconium catalyst based on a Syria surface. So there are basically 3 steps where this can be applied. First of all, they need to obtain the potential energy surface. This is the first step. After that, they would need to calculate the reaction rate constant based on this potential energy surface. And finally, they need to apply a kinetic model and compare it with the experiment. So this is the full story of it, basically. Well, I mean, student or anyone interested, there are many more practical examples on how to use DFT. It depends on the software. Maybe I can share the presentation later if there is a need to share it. This website gives you many tutorial and video to use Gaussian. This is for VASP and this is Castor. So in a nutshell, if students are trained to use one of these software, they will be expert in DFT. So in addition to the DFT software, people need to process the data using either Python or any other software that they are familiar with. Okay. Thanks so much. Thanks so much for attending.